Hello everyone, I'm Muhammad Usama, Masters in Mechanical Engineering, and my expertise lies in computational fluid dynamics. That's what I'm going to teach you right now. Well, not really, because I'm going to be teaching you ANSYS, and ANSYS is a computational fluid dynamics tools. It is a black box which lets you have the perks of simulating complicated fluid problems without knowing the theory. However, it is a bit important to know the theory. So I'm going to be talking about the theory in this lecture as well. The problem that we're going to solve on ANSYS is flow around a cylinder or around a ball, around a sphere. You see? It can be laminar or it can be turbulent. It can separate away from the sphere or it might not. It could be anyway. So let's try it out. I'm using ANSYS 2019 model, but it doesn't really matter because the problem that I will be solving can be solved on any model of ANSYS, even 2012 and 2014. So I'm going to use the module ANSYS Fluent. This is really common. This is available on all models of ANSYS. The first step is to draw the geometry. I want to draw a geometry of a ball or a sphere surrounded by a domain which can be rectangular. I can either import my geometry which has been drawn on any other software like SolidWorks or Creo or Proe, Element 3D, 3ds Max or any other software. Or I can make my own. So that's what I'm going to do. I'm going to make my own using Design Modeler, which is built in with ANSYS. Notice the red dot in here and it says starting design modeler. This means that ANSYS is working right now. You shouldn't be double clicking anything while ANSYS says that. Now I want to draw my sketch. Here is my plane. Here are the planes. On the XY plane I want to draw my sketch. So I'm gonna turn my view normal to XY plane so that I can see the XY plane. What's normal to XY plane? The Z axis. So I click on the Z axis. Now I start sketching. First things first, what I want to draw is a circle, a 2D simple circle. What should its radius be? Let's say for now 0.1 meter. Simple enough. It's really small, right over there. Now I want to draw a rectangle around it, right? I want this rectangle to be 0.5 meters away from the center, and I want its horizontal length to be 1 meter long. So now it is symmetric. I want its vertical, select vertical from here. I want its vertical length to be 0.5 meter, and I want it to be symmetric, 0.25. Now we have our sketch. Now to convert this sketch into a surface, we're going to select the sketch, go to Concept, Surfaces from Sketch. Notice the yellow thunderbolt sign over here. This means that something needs to be updated. Surface has been created, but it hasn't been updated. So you right click it, click on Generate. Now it has converted to a green colored tick mark. But note that when we go here in our parts and surface body, it says that this yellow colored domain is a solid. It's not supposed to be a solid. This is where the flow is happening. This is where air or water is supposed to flow. And so we change it to fluid. Our geometry is complete. Close it. And now you open the mesh. Notice the same red dot. Starting mesh in ANSYS is working right now. Don't double click anything right now and wait for the mesh to open. Just keep waiting. It's opening right now. It has opened right now, but it's not fully loaded yet because I don't see anything on the screen. It's just a blank gradient. Now it has loaded. The same yellow colored thunderbolt sign. It means that the mesh needs to be updated, generated. So I don't know if you guys are familiar with the concept of what a mesh is or not, but I'm going to explain it anyway. This is really dumbed down, by the way. So Any computational complex fluid problem is solved by dividing the whole domain in which the flow is happening into small pieces, cubes or squares or triangles or quadrilaterals or any other shape. Over here you have squares and a bit of triangles as well. So in each of these cells, this is called a cell or an element. In each of these cells, the same fluid conditions, the fluid equations are going to be solved, and they're going to be solved starting from here where the fluid enters and flow starts all the way over to the end. But this mesh is really big, and the bigger the mesh, the smaller the number of calculations, naturally, because each cell has its own calculation. Remember, the bigger the mesh, the smaller the number of calculations, and therefore the worse the results. So we want smaller mesh, but not too small, because when we go too small, it means that the whole ANSYS solution is gonna take too long. So we don't use mesh that is too large, so as it would make the solution really inaccurate. And we don't want something, wait a minute, what happened to my screen recorder? Yeah, right over there, it's still alive. You don't want a mesh that is too big, and you don't want a mesh that is too small. You want something in between. Now, how to find the right mesh size is going to be a big lecture of its own, and we don't want to get into that. So for now, we just gonna reduce the mesh size. It is currently too big. It is 5.5 centimeters to 0.025 meters. And we generate the mesh again. This is a reasonable mesh size, but notice that around the ball, the fluid flow is actually kind of complex. If you are familiar with the concept of boundary layer, you know that flow around the ball or around any boundary sticks to the boundary, and there are sharp gradients in there. So around the boundary, we want results to be a lot more accurate. We want to see the boundary layer around this ball, and this mesh is just too big for the thickness of boundary layer. If you are familiar with boundary layer thickness, you know that the boundary layer thickness is really small typically. So what do is we artificially create a bunch of layers. This is done by inflation. Now notice that ANSYS is asking me to do two things. Select the geometry and select the boundary. This whole thing is the geometry. How do I select it? It can be a body or it can be a face. Look at these icons in here. This one selects the whole body. This one selects the whole face. This one selects the edge. This is a face. So I'm gonna select the face selector and go here, apply. In the boundary is an edge. So by default, ANSYS has given me the edge selector, but even if it doesn't, you go to the edge selector, you pick the edge selector and edge selector, and you click on the boundary. Go apply. But how do you maneuver inflation layers? How many layers around this ball do you want? Inflation is ultimately a bunch of layers. How many layers around this ball do you want? What should the thickness of those layers be? How many layers should there be there? There are three ways to implement the boundary layer, the inflation. Look at this: total thickness, first layer thickness, or smooth transition. I would love to go into all of them, but right now let's stick with first layer thickness. It's asking me something yet again. What should be the thickness of the first layer that sticks around the boundary? Let's say it is 1 millimeter. How many layers should there be? The number of maximum layers. Let's say there should be 8 layers. What is the growth rate? Let me explain what growth rate really is. The first layer is 1 millimeter, but the second layer, if we selected 1 as a growth rate, the second layer is going to be 1 millimeter as well. But we wouldn't want that. Why would we want that? Because we want the second layer to be a bit bigger than the first one. Because look at this mesh size. We want our last layer to be almost the same size as these mesh. So we select 1.35. What this means is that each subsequent layer out of these 8 layers, the first one is a millimeter, the second one is 35% bigger than a millimeter, the third one is 70% bigger than a millimeter, and so on. No two subsequent layers are equal in size. Let's update the mesh yet again. Notice the yellow thunderbolt sign. So these are inflation layers around this cylinder or around this ball. The last layer is visibly bigger than the first one because it is 35% bigger than its previous layer. This is how inflation layers work. One thing remains. What exactly is going to be our inlet, our outlet, and the boundary around which the flow is going to flow? We need to tell ANSYS these things, and we need to tell it now. This is the wall, the edge from where the flow is supposed to enter into the domain. So we go to our edge selector, we click on it, right click, name selection, call it inlet. And you need to call it inlet, don't call it something else because you're a beginner. There are reasons for that. I don't want to get into them right now. We go to the outer edge and we call it outlet. This is where the flow is going to leave this domain. What just happened? Yeah, that was just a view thing. So, and this is the boundary around which the flow is supposed to flow. We call it boundary. Here are our name selection. Inlet, it's showing me the inlet, the outlet, and the boundary. Close the mesh now. Notice the same yellow thunderbolt sign again. It means that mesh has not been updated as yet. So click on update and wait for it to update. Notice the same red dot over here. It means that ANSYS is busy right now. It doesn't want you to click on anything else. Do not click on anything else or ANSYS might crash. And done. Now we can move towards setup. Setup is arguably the most important part of the ANSYS simulation. This is where you tell ANSYS what the problem exactly is that you want to solve. In the geometry, you created your geometry. In the meshing, you broke the geometry down into small pieces so that ANSYS can solve and digest your problem. But in setup, you tell ANSYS what exactly are the materials that it needs to work with. Is it water, or is it air, or is it a gas, neon, helium, anything? Or when it comes to solid, is it aluminum, is it steel, is it carbon, is it diamond? And that's the stuff you need to tell ANSYS in your setup part. The first thing that you need to select is the model. Now look at this, energy. When you check energy, ANSYS is going to account for temperature changes, but we don't want to do that in this problem, so we're not gonna mess with it. Yeah, if you have turbulent flow, it is preferable not to select the laminar condition. It is preferable to go with K epsilon, K omega, or SST. But inviscid condition is just too simple. It's too simple. It's for kids who are just getting started with fluid dynamics. We're gonna stick with laminar flow, viscous laminar flow. Next thing, how do you change the material? Your fluid is air. How do you change that? Double click. Go to database and all the way down here, click on liquid, copy, close, close. Go to cell zone conditions and change your fluid from air to water. And now air can be deleted from the system. It's not being deleted from the database. If you want to add air, you can add it. Don't worry about it. So now we have selected water as our working fluid. Now you set the inlet velocity. You set the name inlet, the name selection that you just did. That's this inlet. Now you set the inlet velocity. Let's say that the water is entering this thing at 500 meters per second, just for the lols, really high velocity. Okay, and the outlet is by default a pressure outlet, and it's asking me for gauge pressure. By default it is 0. If I set a gauge pressure, it means that the outlet is going to be pressurized and it is going to resist flow, reduce pressure difference. If I add a negative value in here, it would cause suction. The gauge pressure will be sucking the fluid towards itself, and it's going to increase velocity. For now, we're going to leave it at 0. All right. Close down the boundary conditions and move all the way to calculations. Now, ANSYS solves problems iteratively. For this problem, let's say that we want to solve 1000 iterations. Right click on it and say initialize and calculate. ANSYS is now solving your problem. It's doing iterations. You can do this thing manually as well. When you study computational fluid dynamics, you are taught how to do it manually, and you know what exactly ANSYS is doing right now. It is solving really big, complicated matrices right now. Wait for the solution to complete or for your iterations to run out. And done. Close it. Our iterations are completed, and look at the graph, in fact, before you close it. It's repeating again and again and again and again. So if ANSYS were a person and it was smart, it would stop solving the problem after this. It would know that the solution is repeating again and again and again and again. So it wouldn't need to solve any more because it would know already that the solution is going to be the same. And that would be called solution convergence. Ideally, the solution should have stopped around 350 iterations, but it didn't. And I'm gonna go into the reason for that. Probably I'm gonna go into the reason for that. Right now, you just need to close it. Setup has a green tick mark, which means the setup is complete. But why does the solution have a green tick mark? We didn't open this. Why does it have a green tick mark? The reason for that is that the setup was just the selection of our material and boundaries, but we also solved the calculations. That is why that iteration graph was plotted. In the setup, we did the solution completely. ANSYS actually keeps the setup and solution separate because many times in complicated problems, when you're doing your research, for example, on some complicated geometry, this problem is really simple. If you're doing a complicated problem like, for example, simulating an engine, you sometimes take days, maybe months to do a single project, to complete a single project. It takes a lot of time. So the solution is separated out so that you can pause your calculation anytime, save your work, and start next day where you left. You might have to do millions of iterations. We just did 1000. Anyway, this is the sweet spot. The results, those fancy contours and streamlines that you see all the ANSYS people drawing. Now it is time to see them. This is the reward. Let's draw a contour. What exactly is a contour? A contour is going to show you the values of a property at all locations in the domain, close to the boundary, away from the boundary, around the inlet, around the outlet, away from the inlet, away from the outlet. You're going to see any variable you want or any property you want everywhere. Let's start observing pressure. Let's say we are making 250 contours. Click on apply. Oh wait, yeah. Where do you want the want to see the contour? You want to see it in all of the space. So in this drop down, look at this, the boundary. You don't want to see the contours just around the boundary, not around the inlet, not around the outlet. You want to see it in the whole face. This is the whole face, symmetry 1. So click on symmetry 1, click on apply. Oh my god, this is the pressure. We're gonna get back to it. For now, let's hide it. Here's the contour, click on tick mark, it's hidden. Let's create another contour. This time, rather than pressure, make a contour of velocity. Same deal as always, not the boundary, click on symmetry 1. We want to see the velocity on the whole face. Click on apply. OMG, this is the velocity. It looks pretty, but there's a lot of engineering stuff going on in there. A lot of Bernoulli's equation and Venturi relationship and Navier-Stokes equations. If that stuff feels overwhelming, you need to read a lot more books. And I'm gonna ask questions in this lecture. Let's make something called a streamline. Now contours give you the values of a property all around the domain, but streamlines do more than just that. Streamlines show you the path that the flow follows. So let's say that we are making 250 streamlines and click on apply. Look at that. Look at that. This is the path your flow lines are gonna take. They come in here. Even before they touch the surface, they bend away from the boundary. And as they move away, they start coming back. They start coming back towards the center. The flow starts stabilizing. This is how the fluid is flowing. Now go back to the pressure contour that we first made, the first contour that we made. This is the pressure contour. And there are a lot of things going on in here. Now, what is this thing? What is this red mark over here? What on earth is that abomination? Can you guess? Can you come up with a name for this really high pressure region? It is red in color. Look at the palette. Red color is high pressure. Why is the pressure high just when the flow strikes this ball? Why is the pressure high? I'm gonna give you 5 seconds to guess what this pressure is called, what this high pressure is called. 1, 2, 3. Screw it, I'm not gonna give you 5 seconds. This is called stagnation pressure. You must be familiar with this. You must be. This is the stagnation point where the flow strikes a boundary. It's obvious, it is fundamental. Every engineering student needs to know what the stagnation point is. So, at the stagnation point, the pressure is really high, but you must also be familiar with the Bernoulli's equation. What does it state? That the sum of static pressure, the dynamic pressure, and the head is a constant. In this case, there is no head, there is no height or rho gh. We're working with air, so the rho, the density, is really small. Any height does not matter. So there's only static pressure and the dynamic pressure. Notice that static pressure is simply pressure and dynamic pressure is caused by velocity. So by Bernoulli's equation, knowing that the static pressure is really high, the dynamic pressure, in order to keep the some constant, is supposed to be really low, which means that the velocity at stagnation point, where the static pressure is at its highest, at its maximum, the velocity is supposed to be at its minimum. And we can observe that in the contour for velocity. At stagnation point, the velocity is at its minimum value. It's almost zero. Look at this. Minimum velocity, maximum pressure. This is the stagnation point. Another thing you need to notice is that the inflation layers that we drew around our boundary, they paid off. Around the boundary you see a zero velocity layer, and when you really zoom in, you can see that the subsequent layers after that zero velocity layers start increasing in velocity. It starts going from blue to a little light blue, and then green, and then yellow and orange. You can see that, which means that at the boundary layer the velocity is zero, but away from the boundary layer the velocity slowly increases. But what the hell is this abomination behind your boundary? This whole region. Why is the velocity really high over here? Why is the velocity extremely low over here? Why is the velocity moderate inside this low region? What abomination? What the hell? What the fuck is this? You need to know the answer to that. This exactly is the wake region. You must know this. The wake region. The region behind the boundary. The wake region. You can see it in the streamlines, you can see it in the pressure contours, you can see it in the velocity contours. But there's a lot more to it. Notice that there is this high velocity region inside the wake region, even though the wake region is supposed to be low velocity. Why is this happening? What exactly is this? The answer can be seen in the streamline contours. Have a look at this. This isn't just any ordinary streamline. This is rotating. It's circular. It is rotating. This one is rotating clockwise. This one is rotating anti-clockwise. Why is it rotating? Why is this thing spinning? Because in the wake region, the pressure is low. Both velocity and pressure are low. And what does low pressure do? It sucks air towards itself. It's pretty obvious. What does a vacuum do? It sucks air towards itself. That's how a syringe works. You pull the syringe and it sucks any fluid into itself. That's how blood is drawn with a syringe. So this wake region has low pressure and it sucks air inside it. And it sucks it with such a high magnitude that it starts rotating. These two big rotating objects are called vortices. Vortices. You need to know the terminology. They are called vortices. They're large eddies. They're also called eddies. But the more commonly understood terminology, the correct terminology, would be vortices. Now, as you can see, one of them is rotating counterclockwise, one of them is rotating clockwise, which means that in the middle there is bound to be a level of constructive interference of its streamlines. Both of these velocities, the velocity at the end of this vortex and the velocity at the end of this vortex, are traveling in the same direction. As you can see, when they are traveling in the same direction, it means that there is bound to be a constructive interference. And that is why inside this region, at the ends of these vortices, the velocity is high. And this is the question I just asked in the velocity contour. This thing is caused by constructive interference of the streamlines of each vortex. You see that? Now, why the hell is velocity high in this region? Why is it red? Maximum velocity. Why is the velocity high in this region? Because the wake region has effectively reduced the area around it, the remaining area. Over here, all of the area is available for the flow. But as we go here, the wake region is subtracted from the total area available. And when area increases, we know from the conservation of flow or the continuity equation that area into velocity into density is constant. So if area reduces, density is a constant, velocity is expected to increase. That is why this region is red. And around the boundaries, what the hell is happening over here? What the hell is happening over here? This is the boundary layer. Yeah? Not this boundary layer. This one. It sticks to the domain walls. And as we go away from the domain walls, it gets bigger and bigger until it gets to the normal velocity that we entered. Look at it over here. The velocity we entered is 500 meter per second. This green region is 500 meter per second, and this is 0. So it goes from 0 to 500 meter per second quite quickly. This is the boundary layer thickness over here. This whole thing. So I hope, although there is a lot remaining to be learned, I have explained how to create your mesh, how to create an inflation layer around your boundary, and how to guide that inflation layer. I have told you how to change your material, how to change your fluid material. I have told you how to select your model. I have told you how to do your calculation in ANSYS, and I have told you how to study the results theoretically, how to study what the results mean, what is stagnation point, which is very important, what is the wake region, what are vortices. So this must be enough stuff to get started with ANSYS. Now you should be doing, what you should be doing is to study something called von Karman vortex shedding. It's the same thing. It happens in flow around a ball. When the flow is really high and the fluid is really viscous, there is this phenomena called vortex shedding. You need to look into that. It's not happening in this problem. This is a different problem, but it could happen if I changed my setup. So that's what I expect you to look into. So do some projects on your own and get to me with the results. My email address is muhammadusama1034@gmail.com, or you can leave any replies in the comment section and get to me. Thank you. I hope that you will learn a lot more.